What is going on? Alan here, talking about linear and angular speed for you today in this last section of this chapter. So we're going to start talking about a little bit different, some movement here amongst our circle. And of course, I'm going to start you off with deriving these things, showing you why they are what they are, and then we'll do a few examples on seeing how to use them. So let's get to it. So as I mentioned, we're going to be talking about linear and angular speed with respect to our circular forms that we've been talking about recently in that last section. So since we're going to be dealing with circles, I'll start by deriving them from a circle. And then, like I said, I always like to show you where these things came from so you understand how to use them a little bit better and hopefully help with memorizing them. So we're going to start with the distance formula here, which I hope you all remember. To find the distance, you need the rate that you're traveling or speed times the time. So for example, one that we're most accustomed to using is miles in hours. And so a lot of times we'll get a speed is miles per hour. But when dealing with this, we got to make sure that we're trying to find what we want. And in this case, it is the rate or speed. So we're going to actually take this and solve it for the r. And how would we solve for r? Since it's being multiplied, we just have to divide by t. So that means we then have our rate or speed is given by the distance divided by the time. So for example, if I was to say that I traveled 60 miles in 1 hour, that would be my time. Then we oftentimes abbreviate that as 60 mph, miles per hour. So you're already familiar with this, you just have never broken it down like this most likely. And so what we're going to do then is take it and make it look a little bit different. We're going to make it into that circular format, and because we're changing it to that, we also need to use different symbols to denote that we are on a circle. So we're still going to use this formula, which tells us what the rate is of anything. But what would our distance be if we traveled that on a circle? And we're going to be talking about whether it's inside the circle, talking about the angle and how much that's rotating, versus on a line. And remember, on Earth, we live on the outside of it. So even though we think we're going in a straight line, we're actually on a big, giant curve or sphere. And so to find the angular speed, we'll start with that. What would the distance be determined by? Well, the distance we do with an angle is theta, typically. So in order to find this, we're going to say our distance is going to be dependent on the angle that we travel. Okay, that will be the distance that we're going to go in this circle. Right? And over time, time is timeless, right? It doesn't matter what you're talking about. It can be hours, seconds, minutes, months, years, decades. That transcends amongst all of the sciences in real life. So time will always be the same. But so that we don't get confused with just any old rate and where the theta came from, the angular speed, we're going to use a thing called omega. Looks like a W. And that is going to be our quote-unquote new formula, which we're calling angular speed. That r is still there, as is the distance. It's just in a different form for this different form that we're using of a circle. Right? Well then, how can we relate this to a linear speed? Well, that's going to be a distance on a length of what we call a circle. So this time, that distance is going to be determined by this. And if you remember, that was s, or arc length. And so we're going to use that as our distance traveled over our time. And so that we can say that this is also something different, and we can recognize it right off the bat. The linear speed, instead of our r, we will be using v, kind of like velocity. Okay? Now, This one actually has an alternative form because we also know S to mean something else. We also knew that S was equal to R times theta. So if we wanted to, we could say that this is equivalent to R theta over T. And you're thinking to yourself, why would I ever want to replace one simple thing like S with two? Well, for a couple of reasons. R and theta could be what was given, so you want to use those. But we also can use what we just had a minute ago, and that is the purple one up here where we had theta over T. That's what this was. So then I can say that I have R times the theta over T, which was our omega, that W. So this is an alternative to that linear speed that we can also utilize. So when to use what is when you're given specific things. So here they are in more condensed form, given all of the things that we just discussed. The omega, which again would have to be in radians per our unit of time, because our theta is in radians, because of what we said the S was equal to earlier, R theta over T. So a lot of times we will not use that formula. More importantly, these two along with this one. Okay, so just 3 new things in this section. That's it, short and sweet. Let's get to seeing how we can use it. So for this first example, it says, suppose we have a point P on a circle with radius 10 centimeters. So I'll highlight that. They're giving us the radius, and then they're giving us some ray, OP, and it is rotating with an angular speed of pi over 18 radians per second. They want us to find the angle, or theta, generated in 6 seconds, and then the distance by that same point in that same time, 6 seconds. So what do we got going on here? Let's give you a quick drawing so that you can see it, and then we'll start working this out. So there's my circle, and they said that we have a radius of 10 centimeters, so we're not on the unit circle, and they have a ray OP, and it's rotating with angular speed of pi over 18 radians per second. So basically what we're doing here is we have O here, and then P is going to end up, we'll say, starting here and then rotating. That ray, we're going to rotate it at a certain speed. We have pi over 18 radians for every second. Now we can figure out what pi over 18 is in degrees, but it's not necessary. What do they want to know? They want to know the angle. So remember, we have a few formulas that we just derived. Now we need to figure out what we were given and what we want to find. Because remember, I told you one of the biggest kept secrets in math is you need an equation with what you want to find in it. And you want it to be the only unknown in that equation, because then you can solve for it. So what we were given was the angular speed, which is that W looking thing, omega. And remember, that was equal to theta over T. And since the angle is what we're trying to find, then theta is what I want to solve for. So all we have to do to find it is multiply both sides by T. And now we know that our angle theta is equal to our omega W times T. And if we have those two things, then we are done. All we got to do is put them in and make sure that we give them the proper answer and units. So for us, they said that the W was equal to pi over 18 radians per second, and then the time was 6 seconds. So notice what happens is when we start multiplying this out, remember the only time that we can cancel is when we're multiplying, is the seconds will cancel, as will the 6 and the 18 by 6. So we end up with an answer for theta of pi on top, a bunch of ones, and 3 on bottom with a bunch of ones. And if you wanted to put a unit measurement, you could put radians, but remember, it's not necessary. So our answer is simply pi over 3 radians. Or you should know that as what degree measurement? Good, 60 degrees. So go ahead and pause it. See if you can figure out part B using any of the formulas, and then we'll keep moving on. All right, now hopefully you gave it a try, and I wanted to pause there and let you try part B because this one isn't as obvious because of the 3 formulas that I just derived with you and gave you, this isn't one of them. Remember, those were for linear and angular speed per the title of this section. This is asking for the distance. But remember, in order to derive the linear and angular speed that I did with you, I started with the distance formula. So in order to find the distance, you need the rate and the time. And we were given both of those things. Now, just don't get confused. This is a rate, not a radius, even though they both start with R, and we usually use little r for both. We need the rate times the time. Now, they obviously gave us the time right here, 6 seconds. But the rate, if you remember, was up at the beginning, and that was radians per second, pi over 18. That was the angular speed that it was rotating. So if we punch that in, that pi over 18 radians per second, that would work. And that would give us something. But is that what we want? Is that the rate that we need? Because they want to know the distance traveled by P along the circle, not inside of it. So the key is that. Will our angular speed work for this? No, we're going to need the what instead? Linear speed. And so our linear speed, remember, is that V. And there was 2 different variations of it. We had the S over T or the R times W. And of those 2, do we have this or do we have that? And since we have not heard anything about arc lengths, we definitely want to go with this one, which they did give us. So remember that R times W is now our radius and our angular speed that we have both of. So those are the 2 things that I'm going to be punching into there. The angular speed, which we had all along, that was the pi over 18 radians per second. And then the radius length, which they also gave us, which was 10 centimeters. And notice this time when I start doing all of the multiplying and simplifying, I can now find my distance in terms of something that makes more sense to be along the circle on the outside. Because the radians don't really need to be there, notice I will have centimeters. And that makes more sense as the unit measurement. So use that to your advantage to find these things. In this case, we can also cancel the 6 and the 18 to be 3. So we have on top a 10 pi centimeters over 3. The rest of the things are 1s. So our answer is 10 pi over 3 centimeters. And that's it. It's that simple, but again, some of these aren't going to be that straightforward. You're going to have to use formulas within other formulas and even some prior knowledge like I had to use for this distance formula that you should have known from a long time ago. All right, so the last one of this, part C, go ahead and pause, give it a try, see if you can do it from start to finish on your own. All right, hopefully you got an answer and hopefully it makes sense. Look at your units. We're trying to find the linear speed. And they even tell you in centimeters per second. So the linear speed, remember, was our V that we used. And it had the S over T or the R times W. So we actually already kind of found this, didn't we? The linear speed, we're going to use the R times the W. And our radius, they told us at the beginning, was 10 centimeters. And our angular speed, they also told us, was pi over 18 radians per second. And so because we know everything that we have, just make sure before you go and do any extra work that your unit measurements are going to end up giving you what you wanted. And in this case, what they wanted us to find was centimeters per second. And we don't really need the radians, so that's exactly what we're going to have is centimeters per second. All we want to do is give them the most simplified version of this, and because we're multiplying, we can cancel this by 2 and this by 2 to get an answer of 5 times pi over 9 centimeters per second. And that's it. That's example 1. Doesn't get much easier than this section, but you can get lost within all the formulas, what you're given and when to use what.